In this video, we will learn what a proof by induction is, why it works, and how we can write a proof by using an example. Proof by induction is a very useful proof method when we want to prove that something is true for all natural numbers or for all natural numbers greater than a particular number, let's say 3 or 5. So let's take a look at an example, and going through this example, we're going to see what are the main ideas behind the proof by induction method. Okay, so we're going to prove that for any natural number n, 1 plus 3 plus ... plus 2n minus 1 is equal to n squared. So that is the sum of the first n odd natural numbers is equal to n squared. And to get an idea, let's first take a look at some values and see what happens. And this is always a very good idea to see where we're heading, to see if this makes sense. So for n equals 1, well, 1 equals to 1 squared. For n equals to 1 plus 3 is equal to 4, that is 2 squared. For n equals 3, we have 1 plus 3 plus 5 is equal to 9, which is 3 squared. For we have 1 plus 3 plus 5 plus 7, which is equal to 16, which is 4 squared. And then we can do the same thing for 5. Naturally, we can keep doing 6, 7, all the way up to a million. We're always going to see this pattern. But okay, so far it seems that indeed this is true, that the sum of the first n odd natural numbers is equal to n squared. But this is not a proof. You could do a million of them, but how do I know that the next one is not going to be the troublemaker? How do I know that? I don't. So how do we show that this is actually true for all natural numbers n? Well, I cannot go and check all of them one by one because there are infinitely many natural numbers, which means that I would never ever finish. So we need to find a better way of proving this, one that we can actually finish in a short period of time. And this is going to be proof by induction. Actually, there is another way of writing the proof of this statement, but for the purpose of this video, we're going to focus on proof by induction. Okay, so we want to prove that for any n, like 1 plus 3 plus ... plus 2n minus 1 is equal to n squared. And to make our discussion a lot easier, I'm going to give the thing that I want to prove a name. I'm going to call it p of n. As you see, this depends on n, so it makes sense that the name I give it depends on n. So I'm calling it p of n. And this is a very common practice when we're doing proof by induction, because writing or saying 1 plus 3 plus ... plus 2n minus 1 equals n squared is very long, and it could make the understanding a bit more complicated. So if you do these, then things are a bit shorter and easier to say or read. Now, proof by induction involves 2 steps. So proof by induction has exactly 2 steps, not 3, it has 2 steps. Step number 1 is the base case. And for that, we need to prove that p of 1 is true. So we need to show that the statement is true for the first natural number. And step number 2 is the induction step. We need to show that for any n that is natural, so an integer greater than or equal to 1, p of n implies p of n plus 1. So that is, what we're showing is that p of 1 implies p of 2, p of 2 implies p of 3, p of 3 implies p of 4, and so on. So what this tells me is that if I know that p of 1 is true, then p of 2 is true. And if p of 2 is true, then p of 3 is true, and so on. So you see, in the induction step, I'm not proving that p of n is true. I'm not proving that p of n plus 1 is true. All I'm proving is that if p of n is true, then p of n plus 1 is true. But I could prove this and still have all the p of n's being false. And I like to compare proof by induction with like the effect of falling dominoes. So here we have a picture. You see, the induction step is the idea that if I have all my dominoes aligned, like in this picture, if one domino falls, the next one is going to fall as well. But you see, if I don't push the first domino, none of them are going to fall. So the base case is the action of pushing the first domino, and then the induction step is just the fact that once the first one has fallen, the second one falls, and if the second one falls, the third one falls, and so on. So as I said, the induction step by itself doesn't prove anything. We need both. We need the base case together with the induction step to be able to actually create a proof by induction. Okay, so now let's try to get and put the proof together. So the first thing that I will write down in my proof is we will prove this statement by induction. My reader needs to know that that's my plan, so when they're reading it, they can actually follow easily. Then I say, let P of n be the statement 1 plus 3 plus ... plus 2n minus 1 equals n squared. You see, I'm saying that I am going to give this sentence here a particular name, P of n. If in your proof you start just writing P of n this, P of n that, P of n blah blah blah, but you never tell me what P of n is, I'm going to be wondering, what is P of n? I cannot read your mind. And remember that a proof is an argument designed to convince someone that a statement is true. So your job is to convince me, and not my job to read your mind. So whenever you decide to use a shorthand for your statement, make sure that you say what you mean. Okay, that being said, let's go back to a proof. The base case is easy. We start with n equals 1 and 1 equals 1 squared. Simple. Done. Now the induction step. We need to prove that for any n, if P of n is true, then P of n plus 1 is true. So the first thing that we need to do is fix an arbitrary natural number n. So that's what I do by saying let n be a natural number. And we're going to assume that P of n is true, which is the same as saying that 1 plus 3 plus ... plus 2n minus 1 is equal to n squared. And this is what we call our induction hypothesis. We're assuming that Pn is true. That is our induction hypothesis. And now, under the assumption that P of n is true, we want to show that Pn plus 1 is true, which is the same as saying, well, 1 plus 3 plus ... plus, and now it's 2 times n plus 1, parentheses, minus 1 is equal to n plus 1 squared. And now we just need to massage the expressions to try to go from the knowledge of that P of n is true to then concluding that P of n plus 1 is true. So let's start with the left-hand side of my P of n plus 1 expression, because that's a bigger one, so we have a better chance of manipulating it. So we start with this one, and what we can see, first of all, is that if I take a magnifying glass and I see what's hidden behind those 3 dots, well, we have that 1 plus 3 plus ... plus 2 n plus 1 minus 1 is just 1 plus 3 plus ... 2 n minus 1 plus 2 times n plus 1 minus 1. And this thing in pink, if you look at it, is exactly the same thing that we had in our induction hypothesis. So if I use my induction hypothesis, then what I'm going to end up seeing is that that thing in pink is just n squared. So that's what I'm going to write here. But if my reader is not very careful, they could get distracted and confused. So we need to tell them that here we are using the induction hypothesis. So everyone who reads it, they know where that n squared is coming from. But now you see 2 times n plus 1 in parentheses minus 1 is 2n plus 2 minus 1. That is 2n plus 1. So we end up with n squared plus 2n plus 1. Hey, but I do know what this thing is. It's just n plus 1 all of it squared. Therefore, we have that indeed P of n implies P of n plus 1. Awesome, we have that. So by the principle of induction, we conclude that P of n holds for any positive integer n. So we know that then the sum of the first n odd natural numbers is equal to n squared for any natural number n. And that completes our proof by induction.